Okay, it's time for a follow-up video on sinks so that each video is not 20 minutes long. We're going to look at a more complicated example, and I pose you a question. Remember saddle points? We started with a really nice version of a saddle point that looked like this, and then I had a more complicated saddle point, and our face portrait looked like this. And I said, well, these are kind of the same thing. You just kind of squish it and tilt it a little bit. Well, we looked at our sink, which looked like this. Do you think a more complicated sink is going to look pretty much the same, just maybe squished and tilted? You're going to find out in this video. All right, so what we're going to do is we are going to add one preface, right? There are different kinds of systems. I specifically want you to wonder, will all sinks look the same for a linear, homogeneous, constant coefficient, first order system of ordinary differential equations? Remember, we have 5,000 adjectives that are working for all of chapter 3. Chapter 3 is hard, it's dense, it's tough. It is the nicest kind of system there is, basically. So keep that in mind. Not to scare you, right? But be like, okay, this is not true for every differential equation. We are looking at a specific subset of nice differential equations. Okay? So let's move on. Let's consider a more complicated one. I want you to consider this differential equation system. dy dt equals d times y. How far through the alphabet do you think we're going to get? And here d will be the matrix -2, -2, -1, -3. And first, what I want you to do is I want you to verify, pause the video if you don't want spoilers. If you want to practice finding eigenvalues and eigenvectors, do it right now. Otherwise, verify that these eigenvalues and these eigenvectors, eigenvalue of -4 and -1, eigenvectors of 1, 1, and -2, 1, verify that these are eigenvalues and corresponding eigenvectors. So again, our eigenvalues and corresponding eigenvectors. So that's a good thing for us to do together because we need to remember what that means. This is true if the matrix times the vector equals the eigenvalue times the vector. So we'll start by looking at the left-hand side. What is the matrix times our vector? That's -2, -2, -1, -3, times the vector, which is 1, 1. And what that equals is -2 times 1 plus -2 times 1. Let's remember our matrix vector multiplication. -1 times 1 plus -3 times 1. That's equal -4, -4. Well, is that equal to the eigenvalue times the eigenvector? Well, that's easier, which is kind of the point. Well, the first eigenvalue is -4. The eigenvector is 1, 1. That's equal to, yep, -4, -4. Multiply the 1, 1 vector by -4. It's multiplying each component by -4. So yeah, this eigenvalue goes with this eigenvector. And you can do the same thing for V2. So do the same thing over here. I'm not going to do it right now. It will be. A little spoiler alert. So after that, we're going to take this information and we're going to make our own face plane, our face portrait, rather. So we know what straight line solutions we're going to have. We have two distinct real eigenvalues. And we know that we're going to have straight line solutions in the direction of 1, 1. That's the line y equals x. And also in the direction of -2, 1. That's y equals -1/2 x. All right, so this right here is V1. I'm not going to draw arrows, actually. Well, I will draw arrows, not those kind of arrows. All right, they both have negative eigenvalues, so we're going to be getting sucked in to our equilibrium along both of these. These are solutions themselves. I'm writing them in red and the curves in blue, but both red and blue are solutions. Well, what do you think this is going to look like? Our solutions are going to get sucked to one of them faster than the other, right? Like, I don't know whether the solution is going to look like this or whether the solution is going to look like this. How do we know which one it gets sucked to faster? We have to look at the eigenvalues, right? We know the general solution, right, is going to have, let's write the general solution, right? That's y of t equals some constant times e to the negative 4t times the eigenvector 1, 1, plus some other constant, e to the negative t, negative 2, 1. Which one of these vanishes faster? V1 goes away faster. Okay. So, as time goes on, we're getting really close, or as time goes on, oh gosh, this is actually hard to say. As time goes on, this kind of vanishes, and we're approaching along this vector, negative 2, comma 1. So as time goes on, we kind of vanish very quickly in this direction, and we're left trudging along in this direction. So that tells us that essentially we're going to have things look like this, all going towards our source. Oops. Let's try to be consistent. And we're going to have something very similar looking to our last source, right? As things are all approaching the equilibrium solution, we have our straight line solutions. And which one is vanishing faster? Which straight line solution are we approaching faster? As we go to the equilibrium, what are we kind of moving with? And what we said is this term vanishes much faster because it, in fact, right, this is just, again, this other solution to the fourth power. So that's going to disappear much faster. So really, as time gets long, we're approaching along this vector. Let's approach that question from a different perspective. Okay? So we're curious, another way to think about this is, what is the slope of one of these solutions as t gets really big? Because if the slope is negative 1, as t gets really big, that means we're approaching along this line. If the slope is negative 1/2, sorry, this would be a slope of 1 actually. If the slope is negative 1/2, that means we're approaching kind of tangent to this vector. Well, what are we looking at? We're looking at the slope, and I did not label my axes. Shame on me. We're looking at the slope of this solution, how y changes compared to how x changes. We're looking for dy dx, which is a little bit more complicated here. How does y change with respect to x? I have a function with t. But remember, y and x both depend on t. How do you find the derivative of something that depends on something else? That's implicit differentiation. That's the chain rule. dy dx is just dy dt divided by dx dt. And we can find both of these. How? Well, let's rewrite our general solution. We could rewrite this as a vector. This is k1 e to the negative 4t times 1 plus k2 e to the negative t times negative 2. It's k1 e to the negative 4t times 1 plus k2 e to the negative 2, or e to the negative t times 1. This is our x and this is our y. Oh gosh. I needed that on the next page. Okay, so what is dy dt? You ready for some calculus and you ready for some algebra? Because again, what is the question we're asking is, we want to know, how does this behave as t goes to infinity? We wanted to know that because we wanted to know, are we approaching along this way or are we approaching along this way? What do the curves look like? How can we do this by hand? We'll use technology, but there's some cool analysis that happens here. So what's the derivative of y with respect to t? That's not too bad, right? It's just -4 this minus this. Right? dy dt is just -4 times k1 e to the -4t minus k2 e to the -t. -4 k1, no, yeah. Oh, there's a 2 here, so that, no, we're doing y. Y has no existing coefficients. But what about the x, dx dt? That'll be negative, well, it'll start the same, but then it'll be a +2. Right, this is dy dt and dx dt. Should really have copied down this function. Otherwise, it's so likely I made a mistake. All right, well, let's be good. Let's model good behaviors. Copy down x of t and y of t. All right, x of t was k1 e to the -4t minus k2 e to the -t. And that derivative should be this. -4 k1 e to the -4t plus k2 . I copied it down wrong. This is a nightmare. This is just really showing things that you should do and things that you shouldn't do. All right, what was y? That was the bottom one. They were both positive. And the derivative of y should correctly be this. And it is, great. How does this behave as t goes to infinity? Well, as t goes to infinity, both of these vanish. Oh. And these go to 0. We get 0 over 0. 0 over 0 is not very useful. We could use L'Hopital's rule, but that's also not going to be very useful because derivative of exponentials are just more exponentials. It doesn't make things any easier. You might wonder, can we just say it's the coefficients here? And I'll answer that with a trick. Let's multiply the top and the bottom by e to the t, which is really what we did with polynomials too, which let us do those shortcuts. It's because we did this sort of thing with polynomials. And when you do that, we get -4 k1 e to the -3t minus k2 times 1. -4 k1 e to the -3t plus 2k2 times 1. And now we can see that, yes, as t goes to infinity, what do we get? Well, these go to 0, and we do get -2, -k2 over 2k2. So how does this help us? And this says we can also use calculus to answer the question of which eigenvector, which straight line are we approaching from as t goes to infinity? Well, the slope, oh, I can cancel these k2s, can't I? The slope of any solution as time gets really big is -1/2. So you can really see, yeah, which one are we approaching from as time goes infinity? We have a slope of -1/2. And this is a little weird because, again, remember time is not shown here. So the slope here is -1/2 feels weird because we're going up. But again, we're not thinking about time. We're just thinking about the slope of this curve. And yeah, the slope of this curve is close to -0.5. Slope of this curve as time goes on, yeah, about -0.5. Slope of this curve is about -0.5. Slope of this curve is about -0.5. All right, so forget the arrows. We're looking at dy dx. What is the actual slope of the curve in the xy plane? I know it's kind of complicated. So that's pretty cool. Now you might say, hypothetically, you might say that, Jason, I don't want to do this. Can we generalize this? Can we look at the values of lambda maybe to see how we're approaching? And the answer is yes, but you'll have to wait for it. What do you think it's going to be? Do you think it's going to always be the way that it was here? We'll generalize it in our summary section, which actually might be coming up next. I would have to check my notes, but I'd have to flip them over, and that's too much. Okay. So that's some fun things about sinks. We'll talk about sources very briefly, because we've basically said all there is to say about sources, and we haven't said anything about sources because they're just like sinks, really. Okay. Just in reverse time. We're going back in time for the next video. And then we'll summarize and do a little example, and you will be free. Well, you're free right now. You don't have to watch these videos. I recommend it. But anyway, bye-bye.